Hello folks and welcome to this video. We're going to talk today about some energy conversions and then look at a couple of equations for energy in the hope that we can try and understand what happens when objects move. We'll start by watching a quick video. This is where I get a chance to demonstrate one of the few things I learned at university, which is of course juggling. All right, juggling, one of my favorite sports, because it's fun, but also because it's a really good example of energy conversions. Okay, so let's just think about what happens when we throw a ball upwards. Okay, now the observation we might make is that when a ball is thrown upwards, two things happen. One of them is that its height increases. Obviously, the ball goes from the bottom to the top. The second one, and this may be slightly less obvious, is that its speed's changing. At the bottom, it's traveling very fast, and as it moves up, and when it gets to the top, its speed gets lower and lower until it reaches zero. Okay, so we might make this observation. Its height increases and its speed decreases. Now, we could try and explain this in many different ways. One way might be through using forces. We might understand that the speed decreases because gravity is slowing it down, and that's is absolutely correct. Another way of looking at it would be through the idea of energy conversions. Okay, we know there are two types of energy here. We've got GPE and we've got, which are gravitational potential energy, I should say, and we've got kinetic energy. So what it's worth doing is having a think, where is the energy at its maximum? Where do we have a lot of kinetic energy? Where do we have a lot of gravitational potential energy? If we think about that, we know that gravitational potential energy is the energy to do with height. So the higher up we are, the more gravitational potential energy we have. And you can see that there, the ball at the top has got a high amount of gravitational potential energy and the ball at the bottom has less. And so therefore, moving from bottom to top, we've got our gravitational potential energy increasing. Similarly, we know that the ball as it leaves my hand, okay, is going to have a high speed, and it's therefore going to have a lot of kinetic energy. At the top, we know it's moving more slowly, and so therefore the kinetic energy must decrease. In other words, what we've got here is conversion of energy between two energy stores, which is that kinetic energy at the bottom is becoming gravitational potential energy at the top. Remembering, of course, that our principle of conservation of energy, is always applicable here, that the total energy is always the same. Now, there's quite a lot going on here. So what I think is worthwhile doing is first thinking about these two types of energy individually, and then as we go through it, we can start to combine them and see what's going on here. Okay, let's start from a more sort of fundamental point of view about calculating these two types of energy. As we've said, gravitational potential energy is the energy stored in an object in its position in the gravitational field. Okay, another way of defining it is simply the work done when against gravity when we're lifting a mass through height h. And this leads us to an equation which is as follows: EP equal to mgh. And what I'd like students in my class to be doing right now is in your little equation sheet, logging this equation and then defining the symbols. If you take a second to think about what those are, m is the mass, and that's measured in kilograms. G is the gravitational field strength. So in the case of on the Earth, that would be 10 newtons per kilogram, or maybe 9.81, depending on what precision you want to use. On the Moon, this might be 1.6. On Jupiter, something otherwise. It's to do with the gravity of the place that you are on. H is just a vertical height measured in meters. And it's similar to the distance when you do work. Just specifically, it's an H because we're doing things vertically. Okay, so often we refer to gravitational potential energy as being EP equal to m times g times h. Kinetic energy has a similar definition. It's the work done when we're accelerating a mass to speed v, from rest, I should probably say here. And the way that we calculate it is ek equal to half mv squared. Notice we're doing quite complicated equations here, multiple quantities involved here, some squares, some halves. So we're moving on in terms of the challenge and complexity of the equations that we are using. Here, m is the mass again in kilograms, and v is the speed or velocity in meters per second. So we've got two equations here. Let's just think about how they apply. We can see there at the top, well, if we're at the top there, we've got high GPE because h is bigger, but a low KE because V is smaller. Conversely, at the bottom, we've got a low H and so therefore a low GPE. And then a high kinetic energy, well, that's because we're traveling at a higher speed as the ball leaves my hand. So that kind of makes sense in terms of the equations and how we understand the interaction between these two energy types. Let's finish this short video off by looking at a couple of examples here, specifically of a drone. Let's imagine we have a drone of mass 3 kilograms, traveling at a speed of 100 meters per second. No idea if this is realistic, by the way. At a height of 2,000 meters. Again, no idea if these are actually great numbers, but really we just want to practice the equation here. Now, again, if you're in my class, what I'd like you to do is have a think about trying to calculate this answer to this question. Okay, pause the video, and then when you're ready, press play to see the answer. Hopefully you're ready to go. Okay, the GPE is just calculated by mgh. We've got 3 kilograms. Okay, we've got G of 10. Okay, and we've got a height of 2,000 meters, 2 kilometers, and so therefore we've got a number there of 60,000 joules. Okay, and because we're quite high above the Earth, that makes sense. We've got a lot of energy in the system. Similarly, we could calculate the kinetic energy. Okay, and again, feel free to press pause at this point so that you can have a try and then play again when you're ready to go. Okay, hopefully we've got an answer to compare. EK, kinetic energy, half mv squared. Again, we know the mass is 3. Okay, speed 100. And so therefore, we've got a half of 3 times 100 squared gives you 15,000. Okay, so that's a quarter of the potential energy. These are just two examples. And what you're going to do now is practice a few more examples. And then as we move through, work out how we can use these two equations to predict the speed, for example, of falling or rising objects, and use them in more complicated situations. Thanks very much for watching, and as usual, any questions, please let me know.